Today we're going to do lecture 2 of lecture 6 part 2, which is about sequences and series. As you see, I'm literally uploading it right now on my channel. Also, by the way, I have no views, so no one really cares anymore. Anyway, when I don't see them, there's literally 0 views on my videos. So, at this point, I'm just doing this to get myself, because I'm pretty sure no one's ever going to see these videos. Okay, should probably stop discouraging myself. So, sequence of real numbers is defined as a function of natural numbers which take out real numbers. But that's weird. So, say 1 is 5, second element's 10, 3 is 15. You can tell this is a sequence of multiples of 5. But that's a very weird definition. And just don't think of it like a set of functions. That's the official definition. We didn't know x of n, my x of n, are sequenced by. Many times we just do this, or we do this, more information, and at some point we will just do this, and here's like the sequence details, like 5n or something. So this is over here. This is x of n. So this is actually the more commonly used format. And in lecture 9, I think we're pretty sure we're going to start using this. I've actually not gotten to this point where we're going to start using this. Well, I think we're going to use this in lecture 9. But for now, we're going to be using this. Mainly this one. This one's sometimes used. Oh yeah, there's also one more format. Okay, so we covered all the formats. So now let's talk about examples of sequences. Anyway, how long? Oh god. Okay, that was scary. I never expected that many sequences and series. So, e.g., let's just go quickly. 1, 1, 1, 1, 2, 4, and 1 over n. So, here's how it'd be formally here's what 1, 1, 1 means. X of n equals to 1 for all x. And over here it's x of n equal to 2x minus 1 for all x. And the last one is just 1n. They literally already put it. So how do you formally put these? This actually wasn't covered. But how do you formally put these? Over here. So this is actually sum. So it's actually taking the sum, an infinite sum of ones. Yep, it's taking an infinite sum of ones. So basically it takes the sum of all members in a sequence, and there's actually going to be a formula for that. Do they cover it? Whether or not I know is a mystery. But right now we're not going to take the sum. We're not going to actually compute these. We're just going to represent. This is the formal representation, which I'm going to try to get you used to it. Most of the time, since they don't mention it, we'll just assume n equals to 1 and it goes to infinite. And this is 2n minus 1, obviously. And then the last one is they already literally gave us. It's 1 over n. N equals to 1. Now 1 over n, it's like going to be 1 over 1, 1 over 2, 1 over 3, 1 over 4. So this is actually going to be approaching 2. This is going to be approaching 2. Actually, wait a minute. 5, 6 plus 1 fourth. Don't ask what I'm doing with this. So actually, this is approaching 3. Actually, I'm not sure where it approaches. 1 half plus 1 fourth. All of those approach 1. Maybe it approaches. That approaches 2, so maybe it approaches 3. Anyway, so we are going off track here. So this is important. A sequence xn if bounded if there exists a b greater than 0, such that for all elements in the sequence, or for all n and n, the output value is less than the specific b, which means there's a number which is greater than all the elements. E.g. 1, 1, 1, 1, 1. 2 is a good bound. It's greater than or equal to, so 1 is approaching 1. And 1n is approaching 0. This is already getting close to limits. And at some point, we will understand. Oh, sorry, this is not x, this is n. And you kind of need to see that limit video. Limit video is in Vedic Math playlist. It's at the end of all of my other videos. It's actually unlisted, so you have to just press on the playlist on the end of my other videos. Now here's some non-examples, or unbounded. 2 to the n minus 1. And this is unbounded because it's 1, 2, 4, 8, 16. There's no number greater than every other element because it's going to infinity anyway. And same with just the naturals, or the set of n. Takes out the same n. 1, 2, 3, 4. This is unbounded. And here's the negation. It's nice to take a negation. So here's a remark. It won't be actually the theorem because we already have it. So x to the n is unbounded. They exist. If for all, no for so for they exist goes to for all. So for all b greater than 0, there exists an a and n such that. Oh my God, that was wrong. Well, I'm reading this wrong. Sorry guys, I'm failing all of you. Next set, if unbounded, if there exists for all b greater than or equal to 0, there exists an n in natural numbers such that, like, the output value x n is greater than or equal to b, and like it's just a negation. And here's a proof that n is unbounded, not 2 to the n minus 1, because that was my own example. B is greater than or equal to 0. By Archimedean property, there exists an n in natural numbers such that n is greater than b, which implies n is unbounded. Archimedean property. Definition. Sequence x of n converges to x to r for all epsilon greater than 0. Oh god, this is epsilon m proofs. They're existent. M and n such that for all n less greater than or equal to m, absolute value of x and minus x is less than or equal to epsilon. Since epsilon is positive, we don't need to put epsilon value around it. So what does it mean to be convergent around a number? Well, here's x plus epsilon. Actually, epsilon in this situation, remember how I told you at some point epsilon will be something so small? Well, this is supposed to be a super small number. Epsilon, the precise defined interval, it's a super small interval. It's not like 0.5, 6, 0.001 or something. And the elements are just coming in and slowing down around x. So the elements are just coming closer and closer and closer and closer and closer. So by the way, 1n converges to 0. Because n, if it's -1, that's -1. If it's -2, it's -1/2, -1/3, -1/4. It's converging to 0. So yep, they're getting slower and slower, approaching 0. Theorem. If x is y in real numbers, and for all epsilon greater than 0, y is less than epsilon, less than or equal, so equals to y. Suppose x equals to y. Suppose x and y are in R, and for all epsilon greater than 0, absolute value of x minus y is less than epsilon. Suppose x does not equal to y. Then the absolute value of x minus y is greater than 0. Then by the absolute value of x minus y is less than the absolute value of x minus y divided by 2. This implies 1/2 of the absolute value of x minus y is less than or equal to 0, which implies x minus y absolute value is less than 0, which doesn't make any sense whatsoever. Contradiction. So that was just a theorem. Epsilon is supposed to be super small, by the way. Like super small. Like so small you can't even see it. It's also supposed to be a small interval. If x then converges to x and y, then x must equal to y. So basically it converges only to 1. So after this proof, we'll get on to limits, then we'll be done. Suppose x of n is converges to x and y. Let epsilon be greater than 0. This x of n converges to x. They exist. Oh, by the way, these m epsilon proofs are so common. Like they are commoner than common. Oh, by the way, I forgot to put some of these squares. Let me put some squares. Nice squares. Okay, that was the only square I needed to put. So there exists an m1 in the natural number such that for all n greater than m1, this is like the style of the proofs. For m1, xn minus x is less than epsilon divided by 0. So now since xn converges to y, exists the m2 natural numbers such that, well, we know how it works, such that for all, well, it is for all n greater than or equal to m2, right? This is the style of the proof. Since x is y, for all n greater than or equal to m2. I'm getting so used to these proofs at this point. I was actually just walking around, moving. Xn minus y, absolute value, less than epsilon 1 divided by 2. We're choosing epsilon divided by 2. You can choose anything. Then since m1 plus m2 is greater than or equal to m1, and m1 plus m2 greater than or equal to m2, makes sense. Supplies x minus y cx minus x and 1 2 plus 1 plus xm2, which is less than or equal to and you see how annoying absolute value just gets. You have to write it so many times and you just see absolute value, which is less than epsilon plus epsilon over 2 plus epsilon over 2, which is less than epsilon. Thus, this is very annoying. It's epsilon greater than 0. X minus y is less than or equal to epsilon, which means x minus y is 0. Since epsilon is like the smallest thing, it's the infinitesimal greater than 0, which means x equals to y. Definition. Or actually, that was part of a previous statement of x. Absolute value of x minus y is less than or equal to epsilon. Oh, this is just less than. Definition. Oh yeah, this is the limit definition. If sequence x of n converges to x1, so we'll just put it as like an arrow, or on the bottom, we'll do that sometimes. We call x to be the limit of x to the n, and write x equals to lim n to infinity x to the n. E.g., xn equals to 1 for all n 1 1 1 1 1. So basically, it's obviously 1 because no matter what, the infinite element will be 1. It's always 1. And now here's a very small proof. And I'm, oh, yeah, I started putting squares now. I don't have to put squares. So, proof. Let epsilon be greater than 0. Choose m to equal 1. Then, if n is greater than m, xn minus 1 equals to 1 minus 1 equals to 0, which is defined to be less than epsilon because epsilon is greater than 0. And then we'll do one more limit, and then proof, and then we're done with lecture 6. Lim into infinity 1 over n equals to 0. Proof of epsilon be greater than 0. So let epsilon be greater than 0. Choose m to be a subset of the natural such that 1 over m is less than epsilon. 1 and technically 1 over m exists by Archimedean property. So let n be greater than or equal to m. We all know it's just going to be like a natural number. 1 over n minus 0 equals to 1 over n, which is less than 1 over m, which is less than epsilon, which is the end of the proof. And remark. How do you come up with M? No, how do you prove limit statements? So this is the style of proof, which is it's going to be very important. So how do I prove lim n to infinity x to n equals to x? How do we prove this statement? So first we have to say let epsilon be greater than 0. Then we choose m to be m to equal. Then if n is lower than m, xn minus x. No, there's no dot here, it's just a period. So minus, actually there are a bunch of dots here, sorry. Which is at some point less than epsilon. So now how do you come up with the m? So you have to do something, find something involving m, so just have to get some inequality. Then say involving m, sometimes we use 1 over m, involving m, which is less than epsilon. So now we're kind of done with lecture 6, and now we'll have a bigger discussion on sequences and series. We're gonna have a big discussion. And lecture 7 is gonna get much more serious. I mean, lecture 7 is smaller, but what will lecture 7 be parts? Oh, then I'll talk about we'll talk about more convergent sequences and then monotonic sequences. So anyway, bye. So this was actually a long part of lecture 6.